Hello, in this session we are going to study use of thermistors in electronic circuits. Thermistors are semiconductor devices normally known as NTC devices or negative temperature coefficient devices. So we use thermistors wherever we are going to use temperature as a sense as a sensing parameter for controlling equipments. So we'll start by opening QUCS. As usual, we'll start with a new project. We click the new button and then we type in the name of our circuit. So it's going to be a temperature sensor and create. So the project temperature sensor has been created with a untitled schematic page. We go to the component section and here we don't see a thermistor symbol available. So what we are going to do is we are going to convert a resistor into a thermistor. So we'll select the resistor symbol and drag it, rotate it if you want to have it in the vertical position. Position the resistor by left clicking in your mouse and position another resistor. So we are going to have a voltage divider and so we will need at least two resistors. You don't need more than two resistors. So R1 will change R1 value to at least 3.3K. Click enter to save the. Then we'll change R2 into NTC1. So this is going to be my resistor, my NTC, and I'll change R equal to RT. So it is going to be a variable for which we are going to set our thermistor equations. So I will open this Wikipedia page where you will find details about this thermistor. So this is how your thermistor will look like. So this is the temperature symbol, thermistor symbol, and we come down to its basic operation. We go to the equation which we are going to use. So I am going to use this R equal to R0 into e power minus b bracket 1 by t0 minus 1 by t. I can break it down into two levels, that is R equal to R infinity into e power b by t, where R infinity is equal to R0 into e power minus b by t0. So R0 is the resistance at value of temperature T0, that is at 25 degrees centigrade or 298.15 degrees Kelvin, while T is going to be the temperature at which we are going to measure the resistance. So we are going to use this equation in our thermistor model. So what we are going to do is we can also go to another web page called Canthem. So you will find a table. So a table of different thermistors. So this R 25 degrees centigrade, you will have thermistors with various values at 25 degrees centigrade, and for each thermistor there is a there is a beta value. So this will vary from company to, this may vary from company to company. Each company will give you a data sheet like this. This data sheet belongs to a company called Cantham, which manufactures NTC thermistors. So you can download such data sheets from the manufacturers. So we are going to use this 3 volt uh, uh, this 3 volt thermistor, for which the beta value is 3270. So now I come to QCS. I am going to start by creating this. I am going to insert a equation in this circuit. So I will select insert equation and then bring it down and position it somewhere. So I will double click this equation. The name I will change it as NTC1 equation, and then I will come to Y. So I am going to set the value for beta. So I will type B, and then I am going to type in the value, that is 3270. And now I will click add. What it will do is it will add this B value. Next I will come to another value. So now what I am going to do is I am going to go to this thermistor Wikipedia. So at this level we are going to add our R0, that is, so R0 at that R infinity is going to be R0 into this e power thing. So now I come here and declare R0, that is, I'll call it RZ, and RZ now is going to be 3K or 3000, and I'll again click add to add this. You can click this apply so that you can see the again that the equations are created here. Now we again go to RZ. So this time I am going to define my resistance at that this thing, or we'll call this as, okay, we will now call this as RE. So this is my resistance at 20 degrees centigrade, or I'll call this R25, and or I'll call this RE. So this is more, I will not add a numerical here, it may be confusing for QUCS. So I will just call it RA, and RA is going to be our equation. So it's going to be R infinity into exponential of B my T0. So I come here. So here it is going to be R0, that is 3000 into, you can type in exponential for E, and then it's going to be we are going to add a minus symbol, so I will use -1 into B divided by, I will use this value, that is 298.15. So I go back here, divided by 298.15. and close the bracket. I close the other bracket also and add this. So I have declared RA. Now I have to declare the value of RT. Now I'll wipe out everything in the right hand side. Yes, in the right hand side. So RT will be equal to R0 into exponential B by T. So I now come here. RT is going to be RA I have to take care of the case of the letters. So lowercase r is different from uppercase r. So we have to be careful when we are typing the equation variables. Now RA into exponential beta by, we leave it as t. So we are going to have this variable t. Now we add this equation also and apply. Now we can click OK. So we have set the value for this NTC. So all we are going to do is we are going to vary the temperature and look at the whole thing. If you want, you can position this equation somewhere else like this. Now let us complete this circuit. So we need a voltage source. We'll select a DC voltage source, position it somewhere and change its voltage value to 5 volts. Then we are going to add the ground for the circuit. So we'll select this insert ground. Keyboard shortcut for this insert ground is Ctrl G. We select this, position it. So you can have any number of ground symbols. They are all going to be the same. It's a copy of the same symbol. So this helps in reducing errors while wiring. So for wiring I am using Ctrl E on my keyboard. So you come to the crosswise, you left click on the first connection point, drag your mouse up to the next connection point and left click on your mouse. The connection is complete. Now we repeat it the same way for other connections. Now when you want to change the direction of your wire, you click at the point where you want to change the direction and continue dragging up to the next connection point and click. So like this we have completed we have completed wiring the circuit. Now it's time to name the wire where we are going to measure the voltage. So we'll use this wire label command. Again the keyboard shortcut for this command is Ctrl L. So I have pressed Ctrl L on the keyboard. Now you have this symbol that follows your cursor. You click on the wire. Let us call this A and click OK. So now you have this A. Now it's time for us to go for the simulation. So we are still in the component section. Let's go down to the simulation. So it's going to be DC value. So we select DC simulation. Can position it anywhere in the schematic page. And since we are going to sweep the value of the temperature, we select parameter sweep and position it somewhere here. Now we double click this parameter sweep. So we are going to select the simulation where you are going to use this parameter. So we select DC1 and the sweep parameter is going to be T. And then the temperature, so we start at 0 degrees centigrade. and we go on up to, let us say, 150 degrees centigrade, and we'll have at least 1000. So we'll have at least 1001 number of samples. We can apply this like this. So more number of samples, your curve will be more smooth, but it will also increase the time required for the simulation. So you can choose to increase it to, let us say, 1501. Then you have got 100 point. It will step at 0.1 degree centigrade, and now I am going to, oh yes, we have to convert it to, let us say, since T is going to be in Kelvin, so 0 degree centigrade is going to be, it's going to be 273.15. So it's going to be 273.15, and this is going to be 273 plus 150. So it's going to be 423.15. So we are measuring temperature in Kelvin, not in degrees centigrade. So we apply and click OK. So I think your simulation settings is complete. Let us try going for the simulation. You can either click this gear wheel symbol here, which will simulate, or you can use F2 on your keyboard. I am going to press F2 on my keyboard to start the simulation. So it will ask you to save the schematic file. I'll save the file as temp sense. Now it will run the simulation. So I think we have committed a mistake. It should be in this equation. So I will add the multiplication operation symbol here and click apply. Now let us see. We'll run the simulation again. So that was the error, and we have rectified the error. So now I'll drag the Cartesian diagram, and now I'll select I'm going to measure the temperature at AV. I'll select, I will double click this AV and click OK. Now I got so your temperature is in Kelvin. So this is your temperature. So you want a more sharper curve, you will have to increase the temperature, the resistance value of your R1. So I will change it to, let us say, 4.7k ohm. I'll click enter on the keyboard to complete the complete the value updation. Now I'll click F2 to run the simulation again. Now that I have got a different curve. If you want to see how the whole thing works, then we can have some more circuits. What I will do is I'll select this entire resistance network, Control C for copy, and then Control V for paste. I'll position this here. I'll position one more here. So since they overlap, I'll pull this parametric sweep somewhere. So this is a page with no limitations, so you can have the page as big as possible. Now I'll change the label to B. That is, this wire is going to be B, and this wire is going to be C. Now I'll change this R2 value. R2 value I'll change it to, let us say, 3.3, and R3 I'll change the value to, say, 5.6. Now we will complete this circuit by connecting R2 and R3 to the main circuit, right? So we again run the simulation by clicking. Now I'll select this graph. I'll select B. Sorry, I'll go down and select BB and CV. That is voltage at the B, and so you got you three different values. So the color, you want to change the color, you can change the color. So supposing I want CV as green, double click, go to CV and select the color button and choose a green color. Can choose somewhere like this. Click OK and apply and click OK. So you have changed the color of C. So you see, uh, so as we kept on increase, so you see C has got a lower this thing. So if you want to control, let us say at 30 degrees Kelvin, 300 degrees Kelvin, or let us say somewhere here 25 degrees centigrade, you want to turn it on at that point, then obviously you can set this value. So you may have to reduce the value if you want to change the. So this is going to, that is, the resistance will change with increase in temperature. If you want to the resistance, the voltage to increase with rise to temperature, all you have to do is interchange the position of the NTC and the resistor. So it just will pull DC simulation and all this equation, parametric sweep, etc. I will pull it a little farther. I will now select NTC3, copy and paste. I'll position it. So now I have put NTC4 at the top, and I select R3. I will control C for copy, control V for paste, position it here, and I will have a control G for ground, position the ground just below the resistor, and control E for the wire command, and complete the circuit. I'll call this wire between NTC4 and R4 as D. Now I again run F2. But this time I will leave this diagram as it is. I'll choose a fresh diagram. You can have as many diagrams as you want. So here I am going to choose D and C alone. I am going to select C and I am going to select D. That's all. So this is how your circuit will respond to your. So you see, so you see, so you see D is the curve where the voltage will rise with temperature, and C is the curve where the voltage will decrease with the temperature. So you can use the thermistor in both ways. So now we have sensed the temperature. Now we will open one more. We'll save this. Now we are going to move down to the application of this temperature sensor. So what we are going to do is we are going to go for this temperature sensor and we have another untitled page which I am going to save as temperature control. Right? So I will even keep this temperature sense circuit open. Now what I am going to do is I am going to select this equation and control C. Select this. I will first start with I'll select one of these. I'll select this set of resistor and voltage source set, copy it, go down to temperature controller circuit and paste it. The same way I go to temperature sense circuit page, select the equation, control C and go to temperature control schematic and position it here. So we have brought it. So you don't have to type in everything at this every time. We can copy and paste this. This works easily. Now we'll go to the components. We'll go to the simulations. You select DC simulation, position it here. Yes. We need to add a transistor circuit to this. So I will select transistors from the library. So you have got transistors in your nonlinear components, but these are not manufactured transistors. These are transistors at the concept level. So if you use these transistors again, you will have to set the forward beta and other parameters for the transistors. Instead I will go for a transistor that is available in the market. So I will go to the library. So whatever component you come across in the library are real-time components which are available in the market. So I will go to manage libraries where I can select a component based on its characteristics. So when I click this manage libraries button, I come to this page, to this dialog box where you have these different component sections. I can go down to transistors. Now you see there are a lot of transistors available. So you can select each transistor and see what its parameters are. So this 2N2219A is a silicon NPN transistor which has 800 milliwatt uh, maximum power, dissipation 40 volts between collector and emitter, 800 milliamps maximum collector current, and 350 to 50 megahertz frequency range, and set TO5 package. So we go down to select something that is more familiar with us. You can go and select even BC107A, which you have been using in your lab. So this is a small signal NPN BGT transistor. It has got 300 milliwatts dissipation, 50 volts between collector and emitter, and maximum collector current is 100 milliamps. So, and it is a TO18 metal case. So you again go down, will select one more transistor to see what is the difference. I will select BC548C or BC548, BC549. So this is a low noise small silicon NPN transistor which has got, so it has got that maximum collector to emitter voltage is 30 volts, 200 milliamp maximum collector current. It's a TO92 package. I will go down to, I'll go back to BC107A, because this seems even BC109C is silicon NPN BJT transistor. I'll select 107A, and now I'll drag this transistor to the schematic page and close the dialog box. I'll position this somewhere here. If you want, I can drag this down. You can use the cursor button to drag them like this. Select the transistor and drag it. You can use the cursor button to drag it anywhere like this. So I'm going to have a resistor at the collector junction. I select R1, Control C and Control V. I'll position it somewhere here. I'll select this transistor and position it just below the resistor. Now I'll complete this circuit by turning on the wire command. So R2 is connected to the collector of the transistor, and the base is connected at the junction between the thermistor and R1. You can either draw this emitter to the ground like this. Now I need to, now there are two ways of measuring the voltage across at this point. I can add a new label called, I'll call this B. Now I run the simulation, F2. Oh yes. Oh, I forgot to add this. Uh, Add the simulation sweep parameter. So I go back to simulation, select parameter sweep, and then click open this parameter. In fact, yes, I should have copied it from there, but okay, never mind. So I'll start from, let us say, I'll start from 250 degrees Kelvin, or 240 degrees Kelvin to let us say 500 degrees Kelvin. I'll start at 250 to 500 degrees Kelvin, and I'm going to have 2501 number of samples. I click OK, click apply and OK, and now again run F2. We shouldn't be having any problems. RT. RT is undefined. Oh yes, I forgot to change this to T, right? So these are some errors we may normally commit. So a bit you have to be watchful about this problem. So now it's okay. So we drag the Cartesian diagram, and now we are going to select AV and BV. Click apply and click OK. So you see that your so you see that the value is, so it turns on at around 350 degrees Kelvin. So that should be roughly around, I think it's a little bit more. So we'll have to reduce uh, the control value. So I will go and select this at, I'll keep this as 1K so that the rise will be a bit sharp. I will I'll change this to, let us say 2.2K. Let us see what happens. F2. So it only increases the switching point of the temperature controller. It means I have to increase the value. Let us increase the value to, let us say, about 5.6K and turn on F2. So we should have, if you want, you can increase the x-axis thing. So it turn this step is at 50, you can have it at 25. So it will show it like this. You can increase the size of your diagram so that it is more well. So it is happening somewhere at 337 degrees Kelvin. So this is my circuit. So it turns on at this point. Supposing you are going to add a load here, that is R2 is going to be the coil of a relay or anything, then we measure the voltage using a probe. So we'll go to the probes, select voltage probe, and rotate it so that positive pin of the voltage the probe is connected to the top to at the positive rail, and the negative is connected at the junction between the collector and the resistor R2. Now I again run F2. So I will leave this as it is, or I'll turn on this. I'll go to PR1V. So this is your the The pink curve is your voltage across the resistor. That is, if you had connected a relay in that place, the relay would have been turned off at this point. So if you wanted to change way it controls, all you have to do is interchange the position of R1 and NTC1. So then if you are going to connect a load at R2, obviously you will have to change the position of R1 and NTC1. But if you are going to use the output at B, then you don't have to change this. So this is how NTC is used in a simple temperature control circuit. I hope you enjoyed this session. We'll see again in the next session with a different application. So thank you and goodbye.